We will now proceed to the analysis of viscous flows. So far we have studied integral conservation laws, and during that we have seen how to derive the differential form of the conservation law as well. So in this set of lectures, we will make use of the differential laws and find out how we can find out the distribution of velocities, and correspondingly how we can find out the stresses, and with the help of those we can find out various useful uh, entities like pressure drop or the viscous stress on the wall, and so and these kind of things. So before proceeding, let me just write down the momentum conservation equation. So right away we have the incompressibility condition. So this is incompressibility, and apart from this we have the three momentum components. So rho del u del t plus u del u del x plus v del u del y plus w del u del z is equal to minus del p del x plus mu del 2 u del x2 plus del 2 u del y2 plus del 2 u del z2 plus rho times bx, where bx is some specified body force. It's a force per unit mass. Similarly, we can write down the y momentum equation. So del v del t plus u del v del x plus v del v del y plus w del v del z, and this will be equal to minus del p del y plus mu del 2v del x2 plus del 2v del y2 plus del 2v del z2 plus rho by. And lastly, we have the z momentum equation. So typically, if we are considering flows in which gravity is the only important body force, then we can write down the body force B as 0, 0 minus G. It's as simple as that. Now, oftentimes we will be analyzing the flow through pipes. So, for pipes, it is convenient to have a cylindrical polar coordinate system. So cylindrical polar coordinate system, obviously, I mean, it does not make any difference as to what coordinate system you use, but finding out the solution mathematically is far more easier for the case of cylindrical polar coordinates for flows through pipes. And the primary reason being the conformity of the boundary conditions. So if we were to write this down in a Cartesian form, we would have a very hard time writing down the exact parametric form of the boundary condition. Well, for the case of a cylinder, it's not so difficult to write it down in Cartesian form, but still it is more convenient to write it down uh, in a cylindrical polar system. So let us look at how the Gurney equations look like for a cylindrical polar coordinate system. So once again, the continuity equation is always there. I'm not gonna write it down, but I'm just gonna focus on the momentum equation. So if the components of velocity are Vr, V theta, and Vz, okay, where this is the Z direction, this is the radial direction is R, and theta is defined as the angle swept in the plane. Okay, So we can write down the equation as rho del Vr del T plus Vr del Vr del R plus V theta upon R del Vr upon del theta minus V theta square upon R plus Vz del Vz del Z del Vr del Z, and this will be equal to minus del P del R, that is the pressure gradient, plus the viscous terms. So the viscous terms are basically the Laplacian of the velocity. So this will be del R of 1 upon R del R of R V R, plus the second term will be 1 upon R square del 2 VR upon del R2 del theta 2, not R2, plus del 2 VR upon del Z2 minus 2 upon R square del V R del theta, plus an additional body force in the R direction. So similarly, the other term, so you can identify this as the centripetal acceleration term, and you don't need to memorize any of this. This will be given in the question itself. So this is the radial direction. Similarly, you can write it down for the polar direction. So it will be rho del V theta del T plus Vr del V theta del R plus V theta upon R del V theta upon del theta plus Vr V theta upon R plus Vz del V theta upon del Z, and this will be equal to the pressure gradient in the theta direction. So minus 1 upon R del P del theta plus mu. So then again you have del R of R del R of 1 upon R del R of R V theta plus 1 upon R square del 2 V theta del theta 2 plus del 2 V theta del Z2 plus 2 upon R square del, let me just check with the expressions, maybe I mean memorizing this is a waste of time. So anyway, these expressions are found at the back of any fluid mechanics book, but let me just write it down without any errors. Mm, yeah. Okay. So in this equation, this particular term should be del u phi rather del u theta, while in this equation it will be, this will be minus, and this will be plus in fact. So plus 2 by r square u vr upon del theta, not upon, minus u theta upon r square, v theta upon r square. So these are the viscous terms, and lastly the simplest form is the momentum conservation in the z direction. So rho So I'm not going to write down each of these terms because in the case of z direction we will not have any such terms. So del vz del t plus let me write it down. So vr del r of vz plus v theta upon r del theta of vz plus vz del z. So this is essentially v dot nabla operator in cylindrical polar coordinate system. And on the right hand side we will have equal to minus del p del z plus mu. So the Laplacian in this case will be simple, 1 upon r del r of r del r of v z plus 1 upon r square del theta 1 del theta 2 of v z plus del 2 vz upon del z2. So the z momentum equation is the simplest because it does not have these kind of additional terms. So these will be the primary equations that we will consider in this in the following lectures: the Cartesian form and the cylindrical polar form. The cylindrical polar form I'll type it down and send it to you sometime so that it will be usable as a ready reference. So when we are doing problems of which include cylindrical polar coordinate system, you usually have a flow which is along a certain direction, along a z direction or so. So if that is the case, typically you will have what is called as an asymmet a, a theta symmetric problem. That is, the problem will have invariance in theta direction. So if that is true, all these kind of terms will be zero. Okay, so if those are zero, then it leads to a great simplification of the problem at hand. I mean, there are other assumptions also, but this will be one of the most simplifying assumptions that we will use. So now let us proceed to find out some exact solutions of the Navier-Stokes equation. So exact solutions of the Navier-Stokes equation are not entirely known. There is a very limited subset of solutions that are actually known. And if I write down the equation in vector form, so if in this form we observe that this is the primary issue because of which analytical solutions are not entirely possible. This entire equation becomes non-linear because of this u square appearing over here. This term is linear, everything else is linear, and apart from this we have to always maintain an incompressible flow condition. Not always, but whenever the flow is incompressible you have to do this. If the flow is not incompressible, the statement of the conservation of mass still holds true regardless. But this is a special form of an incompressible flow, and we have seen this from kinematics. So the first solution that we will look at is fully developed flow between two parallel plates, and this flow is also called as a plane poiseuille flow. So let us consider the schematic. So this is in fact, let me draw So we have an incipient flow in this direction. This is the x direction, this is the y direction, and z is this. So the plates are considered to be infinitely long in the z direction. Let the incipient flow be at some u infinity condition. So let the incoming flow be something like this. So now we want to find out how the flow actually develops. So these are all driven by intuition. So let us see what happens when such a uniform flow hits a set of parallel plates infinitely long in the z direction. Let the gap between the two plates be 2h, so that from the center line the walls are located at y equal to plus minus h. So this is y equal to h and this is y equal to minus h. Okay, so when we consider viscous flows, we have to remember that the boundary condition at the wall is that of no slip. No penetration boundary condition is a consequence of flow kinematics, but no slip boundary condition is a consequence of viscosity. So if there is no viscosity, there is no means of transferring momentum from the wall towards the inside of the flow. It's like you having a very smooth roller skates and you are going on the street. If there was no friction, you would keep on going without any obstruction. But because of friction, you are losing velocity. The fact that the road is stationary, that is being transferred to you very slowly. If the road is more, uh, if the road has more friction, then you will experience a larger change in velocity, and that is the same as viscosity. So the effect of viscosity first affects the fluid layers near the wall. So fluid layers near the wall will immediately go to zero velocity. But the effect of viscosity has not propagated, meaning the layers away from the wall will still have this kind of velocity. So this velocity has gone to zero, this velocity has gone to zero, but the core has not yet felt, well, sorry, the core of the fluid has not yet felt the influence of viscosity. So there is a basic question. So if I call this velocity as u core, the question is whether u core is larger than, well, whether it is larger than u infinity, whether it is smaller than u infinity, or whether it is equal to u infinity. And the answer is it will be larger than u infinity. U core will be larger than u infinity, and the logic is as follows. Because of the viscous retardation near the wall, the velocity near the wall will definitely become less. So u near wall will be less than u infinity. If that is true, then I must maintain integral u dy at section AB to be equal to integral u infinity dy at section OO prime. Now, if one part of the velocity profile has become smaller than u infinity, then that deficit in volumetric flow rate has to be made up by an acceleration in the core. Therefore, u core has to be greater than u infinity to maintain the same flow rate. With that reasoning in mind, the next question we have is whether u core is increasing as we go inside the channel or u core is decreasing as we go inside the channel. Let us see how to answer that. As we move further into the domain, there will be a larger extent of the flow, or rather the extent, the effect of viscosity will be propagated more towards the center line. So there will be a profile something like this. So now there is still that core. So this is the core, and these regions have experienced the effect of viscosity. So the effect of viscosity, as you give more and more time, it will propagate towards the center line. Okay. So another analogy that you can make is you have a pack of cards. You have a lot of cards over here, 52 in a deck. So if you're moving the entire deck and the first card comes in contact, the entire deck will keep on moving, but the first layer will become stationary. That first stationary card will slowly transfer its momentum to the second stationary card. So it's like fanning a set of cards. So if you've seen those things on television, like when they play poker and casino and all that, not that I endorse playing all those games, but when they fan out the cards, the effect of that card to card friction is spread out over different cards. So the topmost card immediately does not feel the effect of the table. It feels it much later, and it feels it much later. That too through the influence of viscosity through all the other cards. So the effect that the bulk will feel of the viscosity will be because of all the fluid layers from the wall to the bulk. So if this is true, then a larger amount of layers have seen the effect of viscosity. So the velocity retardation has increased from this small layer to this larger layer. And if that is true, then the core velocity has to correspondingly increase in order to maintain the same volume flow rate. So u du core dx is greater than 0. That is, as x increases, the core velocity also increases. But can it increase indefinitely? So if I draw the locus of those points after which the velocity is uniform, that is, it is the core velocity, I can draw something like this. So let me draw the section over here. It's like drawing a pair of brackets. It's easy to draw one end, but it's seemingly difficult to draw the other. Okay, fair enough. So now the effect of viscosity is even more. So if I draw the locus over here, it will be this point. So after this point, there is a core. That is, the velocity has not, the fluid has not felt the effect of the wall. Then lastly, there will be a point where the effects of viscosity would have propagated throughout the distance h. So lastly, you would get a profile like this, where the core is reduced. These 2 points are shrinking and they reach this singular point. So if we draw all the points where the velocity is the core velocity, we would obtain something like this. So these regions have viscosity. I mean, not, they don't have viscosity, but they are sort of propagating the effect of viscosity. The core region is inviscid, hence it is called as an inviscid core. Now at the point where they merge, that particular length that the flow takes in order for the inviscid core and the viscous layers to merge, so this length is called as the entrance length. Beyond this, the flow profile will experience no more changes in flow profile. So after this the profile will be identical. It will be this kind of thing. It will not change as x increases. So this region is called as the fully developed region. So in the fully developed region, u is not a function of x. But as you can see from the diagram or the schematic that I've drawn, u will be a function of y only. However, in the entrance regime, or the entrance region, u is both a function of x and y. So in this region, u is a function of both x and y. Over here, u becomes only a function of y.